Hello everyone. Let's look at the Gauteng 2024 March paper, specifically the multiple choice questions for momentum. Question 1.2 reads, an object is dropped from rest and after falling a distance x, its momentum is p. Ignore the effects of air friction. The momentum of the object after it has fallen a distance 2x is. Now, the examiners want you to think that it's 2p, but the answer is not 2p. Let's look at why. So let's start off by drawing a sketch. So we can have some building, and here's our object. Let's say it's a ball. Now its initial velocity is 0, and that's because they tell us that it's released from rest. Now it falls a distance x, and it hits the ground with some velocity. Let's call it v. And of course, there's acceleration or there's gravity acting on it, so there will be an a value. Now we can calculate the momentum of an object by using the formula P equals m times v. And this velocity is the velocity that it hits the ground with. Okay, now using these quantities, we know vi, we know a, and we know the displacement is x, we know the final velocity is v. We can use an equation of motion to kind of map out what the change would be. So the only equation of motion that doesn't involve time, because time is not mentioned here, is going to be the formula vf squared equals vi squared plus 2a delta x. Let's sub in our quantities and see what we get. We know the final velocity is v. We call it v. So v squared is equal to, the initial velocity was 0, so 0 squared, plus 2a, and it fell a distance x, so 2ax. Now, if we wanted to solve for v, we could say that v is equal to the square root of 2ax. Now, you may recognize this formula from grade 10. This is also written as v equals the square root of 2gh. It doesn't matter which one we use, it's the same thing. So this is the equation that we're going to be looking at. Okay? Now, let's look at what happens if we double the distance. So our new equation, so v new, our new velocity, is going to be the square root of 2 times the acceleration, but now times 2x. Now, because this is all under a surd, we can take this 2 out in front. So we can rewrite this as, so the v new is going to equal the square root of 2. So when you take it out, the square root stays. The square root of 2 times the square root of 2ax. But we know that the square root of 2ax is v. So the new velocity is going to be the square root of 2v. So that means that the momentum will be m times the square root of 2v, which is the square root of 2mv, then we can just say square root of 2p. So in this case, the answer is B. Now what I want to show you is another way that we can do this, and a way that we can generalize this. So for an object that is released from rest, we just said that the velocity is equal to square root 2ax, right? So the velocity at which the object hits the ground. Now, let's say that the height is changed by some value. So let's say it's changed by k. So we'll say the height is changed by a factor k. Now what we can do is we can say the new velocity is going to equal the square root of 2a times k times x. And we can do the same thing that we did earlier. We can take the k out, and that will be the square root of k multiplied by the square root of 2ax, which means that the new velocity will always be the square root of that factor that we changed the height by times the initial velocity. Now, let's look at some actual cases and understand what that means. So here, if the height was doubled, like it was in this case, then the new velocity will be the square root of 2 times the initial. If the height was tripled, then the new velocity will be the square root of 3 times the velocity. If the height was multiplied by a factor of 4, then the new velocity will be the square root of 4 times the initial velocity. Square root of 4 is 2, so 2v. Now this also works if it's reduced. If the height was reduced by a factor of 4, so a quarter x, then the new velocity will be a square root of a quarter times the initial velocity. And that's half. And remember, this works for any object that is released from rest and you are changing the height. Now, let's look at question 1.3. The graph below shows how the momentum p of an object changes with time. During which one of the following time intervals, measured in seconds, is the magnitude of the net force acting on the object the greatest? So let's look at the quantities that they're speaking about. So they are talking about F net. So let's write F net. Let's look at the quantities on our graph. We have time, so delta t, and then we have momentum. So let's call that delta p. Now there is an equation that we know that uses these three quantities, which is F net times delta t equals delta p. Now, we know that with straight line graphs, we often calculate gradient. So in this case, the gradient of this graph, right, if you had to work out the gradient, it would be y over x, or the change in y over the change in x. Now, on our y-axis, we have momentum, so delta p, divided by, on our x-axis, we have delta t. So we can rearrange this formula by taking this over. So F net is equal to delta p divided by delta t, which is the gradient. So if they want to know where is F net the greatest, all we need to look at is where is the gradient the steepest. And we can see that the gradient is the steepest in this region. So it is from 3 to 4 seconds. The answer D.